All right, good afternoon. Today's talk, we have Klara Nahrstedt from the University of Illinois Urbana-Champaign. And her title of the talk is going to be Campus-Specific Cyber Infrastructure Challenges and Solutions for Scientific Instruments and Their Workflows and Lab Environments. And I'm going to turn it over to Klara so that she can talk more about that. So take it away, Klara.
Yeah, thank you very much, Jason, and welcome to my presentation. I'm going to talk about some of the research that myself and the group around me in terms of faculty and staff and students are conducting now for the last 4 years, coming together around scientific instruments and their workflows and environments, particularly for material scientists and semiconductor fabrication researchers. The real beginning of the overall problem and space was that we actually did start to see increasingly data-driven and interdisciplinary research for scientists, where many of the instruments, experimental instruments, have been interconnected and communicate with each other to actually store in real time. Data capture was a major goal. And we are also seeing that many of these digital microscopes, which I'm going to actually mostly address, are actually very sophisticated scientific instruments with many sensors besides cameras taking images. So it got very, very interesting for us because many of these instruments in laboratories on campuses are taking very diverse type of data, from images to 2D points which need to be analyzed and processed. So when we looked at these environments, and here at the University of Illinois, we have two major laboratories with scientific instruments, the Material Research Laboratory and also the Micro Nanotechnology Laboratory. But on the campus, we have also broader Beckman Institute, IGB, and others. So we did see a lot of sort of newer instruments that have been connected to some storage capabilities. Very often students, staff members, and also faculty would upload data into the public Dropboxes, boxes, local servers, laptops, and even in many, many cases, people would just use memory sticks. And of course, some of the older instruments would even not be connected for security reasons, often to any of these public storage capabilities, and so they would run offline, and so students and faculty would actually just put memory stick and upload the data. So this was actually a situation when we got into this space. The second important aspect for me as a computer scientist was, and for my group that does research in computer science, including my colleagues, faculty and students, that we had to actually learn from these material research laboratories and micro nanotechnology laboratories what is some of the typical workflow they work with. They usually create some physical experimental sample, put either different chemicals together to actually produce the particular material, and then sort of prepare this analytical sample from the physical experimental sample. For example, in the MNTL, they will build devices and they put different layers of materials and let the crystals grow to actually develop a device. And then actually they, in these particular instruments, microscopes, SEM-TEM type of microscopes, they will analyze the samples. There are scientific software that allows them basically to take images, add other sensing information, pressure, maybe, and so on. These particular sort of computers, so that are local actually to these massive multi-million-dollar microscopes, they will actually capture the various sensor data, convert them basically into digital analytical data, and then this particular data needs to get basically put into certain formats. Some are in these very digital DM3 type of formats, the images, or into some pairs, key value pairs for experimental setting, temperature inside of the microscope, what is currently going to put the material together or the device together. But also there have been actually, there's an unstructured text where the researchers actually will write notes to them that actually things happened during that particular experiment. And then usually what we have observed on campus here was that they basically put the data from that microscope computer onto the memory stick, and then via SneakerNet basically go to their own office, put it on the laptop, do some interpretation of the data, and if it's a bad result, they throw it away and make a reservation to their laboratory again to actually get another experiment going. So when I have been studying this particular problem 5 years ago actually now, and read some of the reports from the National Science and Technology, there was actually a major complaint that it typically takes 20 years to go from discovery of new materials, fabrication of new next generation devices. And so we actually wanted to contribute to speeding up this kind of discovery and provided by cyber infrastructure for these scientific instruments where scientists can actually in real time and trustworthy manner to collect data and then curate them, analyze them, and so on. So we did believe that this has to happen. And we also have studied then the data that come from this experimental equipment. And one of the very interesting aspects is that the data that they are producing are very long-tail scientific data. It means that the data that they capture from this instrument, if it is X-rays, if it is SEM, TM type of microscopes, are usually quite small in comparison, for example, to from the biological data or atmospheric data. So you can see actually, if you look at sort of the data size, our data in these materials or in devices are sort of more on the long tail data, but there are many of them. These students or faculty or staff go to these labs and then just take one image after another under different settings of temperature inside of, or pressure or other sort of type of sensing environments inside of these instruments. Because it's so many data, right, they are really sort of experimenting. Also, when they start then to evaluate the data towards the insight, very often happens that 50% of the scientific findings don't even appear in published literature. They throw away the data and then publish basically the best data. And you never know, in 10 years, some of the data that they have actually seen might be actually useful, but basically they are currently not well managed as in the data management infrastructure, and therefore get lost. So as we looked at again this particular problem, studying it on our campus, and then actually I started to talk to other campuses that have materials laboratories, have micro technology laboratories, certain challenges actually are really emerging. One is that there is a tremendous heterogeneity in the scientific data management and processing, especially in this particular domain. Every scientist, when they work towards materials or devices, have sort of their very unique type of data sets. Also, the workflows, task graphs that currently are being processed over this particular data varies very much, again, depending on what do the scientists and the researchers are actually looking at. The goal truly for many of these researchers is to shorten the time from the digital capture to the interpretation and insights. And one of the reasons is that basically the lab sessions are expensive, right? You reserve hour, 2 hours basically on your microscope, you have to pay for that. And so if there is a very long sort of cycle from taking the data, then you analyze it in your office, then you wait until your advisor gets to see it, or maybe your staff member, and then basically you come back. It just takes a long time. The 20 years didn't sort of seem that long once we started to understand actually what it takes actually to, under current situations, to actually make a real innovation and interpretation insight. So real-time data capturing and acquisition really became a major challenge, and also analytics support to gain insights. Now on campus, then another sort of really interesting aspect came up was that, you know, when you look at industry intel, they usually will have, here is currently the same type of microscope from Carl Zeiss, and everything is doing the same. You look at the campus currently in the MRL and MNTL, our current two labs that we study, there are over 300 instruments and at least 20 to 30 different types of the instruments. So it's truly very, very different situation that the campuses deal with than when you look at some of the industrial labs. The other important aspect is that you have very different groups. When maybe in the industry, you have researchers that basically are working on these instruments. Here, you have novice students, you have senior students, you have staff members, you have different types of professors. And so very different groups are collecting and analyzing the data. And you also have to then understand the whole academic cycle. Here currently the students, when they try experiments, they really want to first just to try something. They don't really want to publish it in some kind of public clouds. They want to have it locally, particularly also in the micro nanotechnology lab. When they do work on devices, they want to first test the recipes as they are developing devices. And so it can take 6 to 8 months until they publish any data and are willing to go public. And so they really need private groups to actually within each other, within the group, students, staff, to actually work privately. So that was actually also very interesting to see the difference in terms of rules regarding secure access to metadata that actually varies very much depending on the size of the scientific labs. And of course also analytical tools on scientific campus labs just very. So we basically, under these particular environments, labs and situations, we started to actually explore. And I want to talk about 3 different type of infrastructures. They are very interrelated and actually are starting to actually emerge into, I think, an interesting ecosystem. So the first thing I want to talk about is the 4-seed system that represents a private cloud execution environment for instrument data curation and coordination. So as I already mentioned, the big aspect for these instruments, scientific instruments, is that the data is very variable, heterogeneous, and different type of workflows will be processed over this particular data and conducting the data analysis workflow. And so the execution environment where this particular data gets processed needs to support workflows. And this is sometimes different to, for example, some of the grid environments that are processing scientific data, but where the scientific data is much more homogeneous, and also the workflows are maybe much more monolithic. So our first goal was to set up a campus cyber infrastructure for new scientific instruments where the data would be actually going from these new instruments or from the instruments running an up-to-date secure operating system to a private cloud. And there basically the data could be stored, run workflows, execution environments until the scientists are ready to move the data to some public cloud, if it is MDF, which is the Materials Data Facility, or it is Amazon, or if it's cloud, Google, and others. So our current goal is really to look at this particular connection between the instruments and the private cloud. So we decided actually for the particular private cloud to deploy microservices, which are actually, I think, the container technologies that really allow very easy way actually to be composed into different task graphs, and therefore allow very variable workflows to manage and to run. So each task then in the workflow is modeled as a microservice. The microservices actually have a very nice property that there is a queue attached to them. And so you could have actually very different workflow running by different users that can actually subscribe to a particular task in their workflow and then run it. And so separate task dependency from task implementation and deployment can be actually utilizing this kind of publish, subscribe architecture of these microservice tasks. So if you look at the whole architecture of the private cloud that we have been working on, is that you basically have on the private cloud, you have a workflow invoker, you have a task dependency servers, and then you have the publish subscribe middleware that actually coordinates the submission of the requests for particular tasks within workflows. And to this particular private execution environment based on microservices runs actually on a distributed resource management. So you can have multiple storage and compute nodes to basically run this microservice capability. To this particular architecture, cloud architecture, we then actually connect the curation, capture, and curation service that runs actually on the computer of a microscope and then uploads the raw data. But we also allow basically that in your office, you can then, once you uploaded your data, store the data in the private cloud, you can actually then go to your office, run a workflow, and extract data and sort of do some other functions as workflows. So just to give you a feel for how does the whole process works in the microscope, we have a web interface, so you can actually then upload the raw data that are coming currently from your scientific interface of the microscope, and you basically submit the request to the workflow invoker. The workflow invoker then goes to the task dependency service and asks which particular task should I be computing on this particular data. This particular task dependency service uploads based on your data what kind of tasks you would like to run. Task A, for example, do indexing this particular data. B, do extraction of hidden metadata inside of that particular image. And then basically the workflow invoker gets a response, go to the task A, the data and the request basically gets moved to the task A, where the task basically gets initiated and the task gets processed, gets indexed, for example, in a MongoDB. And then actually once the task is done, it returns its handle to the task dependency service. The task dependency service then basically further issues request to, and the task basically gets moved to, request gets moved to the task B. So in this particular case, then you report again, I am done with task B, what happens, and the task dependency service says you are done. Then basically the results of that particular uploading and that particular workflow gets then returned to that particular user that issued the upload service. So you can immediately look at it and see what happens. So basically you will get a response. Here is currently your image, and here are some of your metadata that have been interconnected with that particular image. So the challenges for setting up this kind of microservice management are that you do have heterogeneity in data formats and workflows. And so, as I mentioned, we deal with these smaller files, but many of those files and the containers truly lend themselves to that. So we actually then worked on the sort of research side to understand not only the publish, subscribe, execution environment to execute through the workflow invoker, the various services, but also we wanted actually to monitor these microservices and also do adaptation. You could imagine that if there is a workflow and there is a user that currently puts a lot of data and that particular one of the tasks, task A, for example, gets stuck on that particular data, you have other workflows waiting for the task A, and so you could have a certain conflict. And so the microservice adaptation layer truly has to have a capability to either preempt some of that particular task and monitor it and deal with conflicts. And so we do have a whole paper on that. I just wanted to put these slides forward that in these particular publications, we do model the microservice resource model, particularly as these tasks are using queues and workflow performance metric that we are currently aiming to monitor and then also adapt is actually the average delay of each workflow type. And so we are currently looking at a string of tasks as a workflow type A1. We also are looking at some of the parallel tasks B and C could be in parallel and workflow 3B. And then actually our adaptive engine of microservices does take into account what are currently number of customers, consumers for task A, B, C, and D. And then actually it does provide to the execution and to the decision engine information about how long on average workflow type 1, 2, or 3 would take. And so then the decision engine needs to decide, do I cancel some of the tasks? Do I let the user know we are preempting you, and so on. So we built this particular system, and we use actually very much open source type of components. The resource management service, we started with Kubernetes, now basically it's Docker Compose, but we use Dockers as containers, as microservices. We use Apache Zookeeper and RabbitMQ as the publish, subscribe, RabbitMQ, now actually also ZeroMQ are looking at, and the Apache Zookeeper as the task dependency service. And then on top of it, actually, we are monitoring the delays of these microservices, storing the systems data in the InfluxDB, visualizing it Grafana, and then actually the adaptive engine to predict how long these workflows might take inside of the private cloud. We use some of the TensorFlow and decision control using Sci-Fi. So we also try to understand if some of the monitoring and adaptation capabilities are working for us. We did look at some of the materials data processing workflows, very simple workflows. And then actually we looked at some of the physics workflows, the LIGO workflows. If we do sort of that kind of workflows, does it actually still scale in terms of prediction, how long these workflows would be taking? And I showed just, very small set of results, but just wanted to show that on the x-axis, as we have arrival of these various tasks and the requests for data, the processing time, how long these particular workflows would stay in actual time versus predictive time sort of matches pretty well. And it's the same thing with the LIGO. And also we wanted actually to understand that with our technique to really carefully monitor and decide on when to preempt tasks so that workflows don't suffer. Did that particular MPC approach, which is our approach, worked very well versus if you don't do anything, then basically no provisioning. You basically, when you have a lot of users, very diverse workflows, that particular congestion can really drive the processing time quite high. So I want to just very briefly talk about the four-seat system that actually implements this particular set of the architecture of the microservices. We are currently supporting private cloud that hosts this particular coordinator, processes, analyzes, correlates the data, and all of our new instruments running Windows 7 and then now Windows 10 are all connected to the private cloud, the cloud side, and you can basically use it. Several very important services are part of that system. One is uploading from the scientific instrument. You can actually decide, like a smart Dropbox, where is currently your remote on the private cloud remote space, storage space, and then basically you can specify your metadata, what kind of metadata currently you want to capture with that particular experiment, and then you can upload the data in the third step, and you are uploading your images, your big data, and that particular system, actually, as it uploads, it takes the metadata plus the images and stores it nicely in this your space specified. We have two types of uploaders. One is basically the standard uploader, where you actually can specify all the metadata. There are templates. Actually, several of our senior students specify templates for many of the experiments happening on SEM or TM scientific instruments. But we also have a zip uploader. You might have actually a lot of data on your laptop. You want to upload it to our four-seat backend private cloud, and we basically allow that. And then basically that system pulls it apart and indexes it and basically allows the older data that you haven't uploaded from the scientific instrument actually to be searchable. The second important service is really curation. We currently actually are using eBay-like type of interfaces, user interfaces, where you can actually see your images plus your metadata. You can also tag them, annotate them, preview them, either at the microscope side or at your office side. And third very important function is one of the microservice tasks are extractors. Many of these images actually are carrying hidden microscopy metadata, and so we have been extracting those metadata and then index them in the MongoDB so that actually, again, you can search for these hidden metadata. We are using currently under the four-seat execution environment, we are using NCSA Clouder data management system that actually allows us to organize the data, not only for files, which Dropbox and Box and everything else does it, but now basically you are having the capabilities of organizing data sets, organizing collections, and this currently lends itself to this scientific environment. And the last function that I want to advocate in the four-seat is the Jupyter Notebook. We are currently in progress to put it into production. We connected actually the users to a Jupyter Notebook, where the Jupyter Notebook actually is inside of a Docker container. You can reserve through four-seat Jupyter session, and then basically it creates basically Jupyter container for you, returns your Jupyter container URL, then basically you can write the existing Jupyter code, and you can fetch the data from our four-seat storage data management data system into your Jupyter Notebook session. You can basically write your script, get the data, it returns to you the particular data set that you want to work with, and apply your Python scripts, workflows in some way, and then you can sort of analyze the data. And when you are done, you basically terminate the Jupyter session. And the data, whatever you processed in the Jupyter Notebook session, are being returned back to the four-seat storage. So We are currently having storage where the cloud currently works very sort of scalable storage, because we wanted to actually scale as more and more data gets stored and more instruments get online. And then we have a compute layer where currently the microservice and workflow environment is running. So the second important project that I think we really are pushing at this point is data acquisition from aging instruments. This has been a tremendous eye-opener for me, actually, as a computer scientist. You know, when I think about it, we have computers, and after 2 years, basically, I say, oh, students or faculty, let's replace it, right? Same mobile phone, you have 2 years, let's have a new mobile phone. Well, as I started to work with the Material Research Laboratory scientists and with the Micro Nanotechnology Laboratory scientists, they basically, I mean, no, you buy microscope that's once in a decade purchase. These particular microscopes, these particular instruments can last 20 to 30 years. And so some of the instruments are actually running not Windows 10, not Windows 7. They are running actually Windows XP, Windows NT, some of them even older. So we basically have several of these instruments in our laboratories that are still very good. Optics works, everything works, just that the software is old. And as you know, these older operating systems are not being patched anymore. Microsoft basically says goodbye. And what happens is actually the scientific software that drives the microscope, basically that company, being the Siemens, being a Carl Zeiss, being a GE, they actually, after 1 or 2 versions of upgrades, basically also say goodbye. They basically say, we are not upgrading it to the newer operating system, our scientific software. You should buy a new microscope, right? That's the easiest answer. So basically, this is too expensive for campuses. We cannot constantly upgrade the instrument because there's a change in the operating system. So many of these instruments are offline. And so our goal truly was to think about at least some of the older instruments to bring online. And I want to actually talk about one of the approaches. I'm sure there will be more since this seems to be, when I talk to various colleagues on campuses, this seems to be an issue in the scientific community. So we want to actually bring some of the older instruments online and allow the scientists to actually upload their data to the private cloud as well as with the new instruments. So we actually saw not only the problem of the obsolete security, but basically these older instruments get obsolete because they cannot be touched anymore. And so many of the IT personnel that manages these computers is worried for viruses. And of course, when you get viruses, malware, then it destroys the scientific software, and because you are not anymore under guarantee from GE or a Siemens or other companies that produces microscopes, then you basically throw away that particular instrument. So obsolete security is one major problem. Other problem I want to point out that the IT personnel also very worries about malware on memory sticks. Right? You could have a malware and that can actually damage your instrument as well. So bringing these instruments somehow online, but in a secure manner, is very important. The other important issue to consider is that some of these older computers actually have a network card that might not actually match the performance of the cloud in terms of its bandwidth. And that actually then has an impact on TCP/IP, on the timeout, on some of these tuning knobs of the protocols that actually expect that the cloud talks to some modern computers. So performance mismatch can happen as well. So one of the possibilities here, what we actually are exploring is to put an edge device between the older microscopes running older operating systems and the foreseed modern cloud. And there basically then this particular edge computer would actually provide a match for the performance in terms of bandwidth, traffic shaping, offloading, and so on, but also particularly security. It would allow actually user instrument registration, data encryption during uploading, firewall to protect against external threats. So we then started to look at how this kind of bracelet could look like, and we actually are having this bracelet device also designed running microservices so that actually certain tasks like whitelisting, right? You get particular data, you want to check, did this particular data come actually from that particular instrument that you allow only to get the data. You might then want to do encryption and so on. So there could be another sort of microservice that can help run the particular code. And so that actually then very nicely synchronizes with the private cloud to actually do the edge control and the dependency service and so on. You could actually also do some placement. So there are a couple of interesting problems, scientific problems. One is microservice scaling. How many consumers do you allocate for each task microservice on edges? How many instruments do you actually allow to connect to the bracelet edge device? And also microservice placement is because you have microservice capabilities on the edge. If there is a lot of load on the cloud, you could do actually some offloading of some of the microservices related to the devices that you are trying to protect to the edge device. So we are truly sort of looking at this particular capability of that bracelet. And the particular edge device, again, is built with sort of commercial components, open source, because we actually feel that this scales better. If it is, again, the Grafana, if it is the Docker environment, the Kubernetes, it's the RabbitMQ, but also it's the proxy. One of the interesting aspects for us is that for these aging devices, we only allow uploading, we don't allow curation. So these weak sort of computing components that we are looking at, like XP, is running Windows on the Windows a web browser, but that particular web browser, for example, doesn't support HTTPS. So we do have to do a major checking also and have task dockers that are running actually these various checks in terms of user authentication and so on. So in terms of the user authentication from instruments via bracelet, we actually allow the user to specify login. This is all on protected private local area network, where user authenticates with the campus to access the instrument computer. Then user authenticates with the forced uploader via Shibboleth or via sort of forced curator authentication API. And we are trying at this point to synchronize this whole access control for users on these aging instruments to have sort of uniform access control and as they would be logging in actually to a cloud, so that they actually don't even know that there is a edge device in between. One sort of possibility is that this particular edge device not only authenticates with the campus database if that user has a right to access this particular edge and cloud, but also is does this particular user have the right to access this particular instrument? There is a reservation database. And so you can then, when you are authenticated, you can then actually upload your data. That's the only operation that we allow in this particular case. The task distribution through the workload uploader will inform actually the edge device to run certain tasks on the edge, right? This is currently where the task edge runs task A on the edge, task B on the cloud. And then basically the foreseed uploader does request from the microservice of task A to run that particular task. When the results are done, the results are propagated to the cloud, where then the task B basically gets processed. And again, because we have quite sort of uniform design of these microservices containers on the edge device and on the cloud, we can do predictions in terms of how long it will take to be busy with a microservice. And here currently, we have been experimenting with work in progress to predict on a per microservice. And again, the predictions are on the cloud a little bit better, less microservices can be at the edges, can have a deviation. But overall, we have been actually quite happy with respect to the load and the performance prediction. The last piece that I want to talk about that the overall framework, the ecosystem is support is the Senselet project. So very interesting problem arose as we were working with the students and faculty and staff in the micro and nanotechnology lab, where they are working in clean rooms. It was not only that they had to work with some of the older instruments, but when they open the hood, when they work with the various equipment, temperature can change, or external temperature, external humidity in the clean room can have an impact on their experiment. So very often they will take images, they take the internal microscopy sort of data, but surprise, surprise, sometimes these results are different, and not really understanding why. They anticipate that the differences come because of different temperature when they have been testing it, or different humidity. Another really interesting discussion that we had with the staff members in these clean rooms was that it is sometimes very difficult to judge when to do maintenance on some of these microscopes or these instruments. And humidity, temperature changes all externally impact these instruments. So we had really two groups of users that have been really interested in using the data about microclimate around the scientific instruments. And so we actually then started to look at this particular problem and started to investigate that even though the microscopes or these devices are in a wired manner connected to the foreseed, we actually would like around these instruments put sensors, Senselet, connected via Wi-Fi, so that the data can be collected in the Senselet Sense Cloud service. And then from there, basically, either the lab managers could look at the data or students could look at the data, and basically, because all the data are timed, they can actually correlate them with their lab equipment information. And on their particular dashboard, then look for not only the internal equipment data, microscope images and internal pressure and so on, but also the external data. So these are currently some of the sort of the test environments that we are currently looking at in the clean rooms. And the publisher runs sort of at startup, and we also have been putting a component called Watchdog so that we can actually watch if some of these sensors go down, can we restart them, so that we have a strong validity and trust in the typical sensing of the data. So the Senselet framework basically represents Wi-Fi sensors that are wirelessly connected to the campus network, but then basically are connected to the Sense cloud, and then the cloud is connected to the 4C to upload new type of data. The Senselets are basically connected to the cloud via message passing, MQTT, and the data in the Sense cloud are stored in the InfluxDB. These are small amount of data. We are at this point having two types of sensors, temperature and humidity. Those were the first that the lab managers as well as the researchers in those clean rooms basically felt that they have a large impact on their overall experiment. And the Sense cloud also runs instance of Grafana. So these are some of our deployments at this point where we are looking at putting sensors around fume hoods or about spinners or around some of these other type of microscopes sensors, as you can see, S2, S3, and so on. So the sensors that we are currently building to experiment with, because we want to have Wi-Fi sensors, are Raspberry Pis that now connecting to the Android basically are allowing us to put temperature and humidity sensors. And so we currently have 5 sensors in one of the clean rooms where we prototyped them, we put them into a safe form factor, as you can see here on the right side, so that it can basically sit next to the computer, next to the lab instrument, and are collecting data. So we are at this point working also with the lab managers as well as with the researchers to see what kind of visualization of the data will be useful for them to actually have a very valid service. So in summary, I want to sort of conclude my talk. The software availability at this point is there. Publications are all in IEEE digital libraries, and the recent PERC 2019 posters are in the ACM digital library, but the software currently is available production level 4-seat system on the GitHub, and we are very interested that people actually download it and they test it, experiment with it. We have senior research programmers, Steve Constanti, and then also Todd Nicholson, that can provide any feedback and sort of about some of the functionalities and capabilities. All projects are actually described on this particular project website. BRACELET currently is in a testing phase. So we are currently testing it in MRL and MNTL, and we are hoping actually to release the software on the GitHub this year, by the end of this year. If you have any questions, Steve again will be a good contact person. The Senselet, as you could see, is now in the development phase. We are testing and developing sort of further visualization, further test and see actually the reliability of these sensors. And we hope actually that the software, again, when it is very stable and production level, we can then release it actually in spring or close to beginning of summer 2020 for people to try it. And if you have any question, my PhD student Zhe Yang and also senior research programmer Steve Constanti can answer questions. So to finally conclude, the lessons learned have been many so far. As I said, we have been now with these projects, the 3 projects from 4 years to 2 years to 1 year. It allowed us actually to explore some novel cloud system approaches. So a lot of, I think, interesting cloud papers came out of that. This is a very interesting scientific domain that puts new challenges on the private cloud design. We definitely believe that this particular domain requires a three-tier approach from instrument PC to private cloud to public cloud. And if one starts to include the edge, then even a four-tier approach. Bringing aging instruments online proved to be very difficult. As I said, we currently, because our system is web-based, we were looking for operating systems, all the operating systems that actually can run still, even not secure, but browsers, and that proved to be quite challenging. Some of the operating systems are just not running the browsers. And so we currently have an XP connectivity, but we are actually very much looking for connecting the BRACELET edge device for Windows 7. As you know, Windows 7 will start to be patched. It's not clear how much the scientific software will actually go to Windows 10, and we have many of the Windows 7. So in that sense, this is going to be definitely useful actually for the not only Windows XP but now Windows 7 type of aging devices. And the obviously most difficult part was convincing scientists really to use it, and there actually sustainability is a really, really important aspect for users to trust that the system should be used. The data management, we need to make sure that the system, the services are available 5 years, 10 years from now. And so we partnered actually with college engineering IT, and I believe that to achieve sustainability, it's crucial to work with the local IT team so that they can actually take over providing these services to the scientific community on campuses. Thank you so much for listening. This is the National Science Foundation funding. I want to acknowledge many of the collaborators, research development team, and COPIs, and other collaborators that made this whole ecosystem possible. And I also put publications there that we have now available.
All right, well, thank you so much, Klara. This is really great stuff. We've already had a question come in. This is from Joe Breen. Are you looking to use Senselet and BRACELET together to give security for your sensor environments?
We haven't at this point looked into that. It is definitely, at the beginning, actually, we have been thinking that maybe the sensors might connect to the BRACELET edge, but at this point we separated them because the BRACELET is truly serving as a security hull to the protocols and to the devices. So to move, and they have the private virtual LAN connecting it safely and so on. It's all wired. We installed actually for the BRACELET the switches that are currently doing MAC layer test checking that it comes, the traffic comes from those allowed. So we have a MAC layer checking, IP layer checking on the BRACELET. We really did not want to mix it since the Senselet has to explore also these Wi-Fi separate sensors. So we basically looked around regarding sensors, and many of the sensors are Zigbees, are not very scalable. Some of these providers basically say, oh yeah, here are some of the sensors, but you actually purchase service from us to the web, and then from the web you can pull the logs into your 4-seat server. And that's not sustainable, right? I mean, so we wanted to actually explore, would there be some Wi-Fi sensors, and so we split that particular project, but it could be. As I said, we still have a year and a half basically on the on the Senselet. So as the BRACELET gets into production level and we release it, we might start looking into that. But any suggestions would be welcome.
Okay, and Joe has a follow-up on that. Have you explored BRACELET with distributed instruments?
Distributed instruments in terms of the instruments are at different locations. In terms of different campuses. Currently, our
yes, that's what Joe says.
The different campuses. Okay, no, we currently only explore. We set up the virtual private network inside of the material research laboratory and inside of the MNTL, and then at the boundary between the virtual private network and the campus, then we put the BRACELET server that checks, and on the virtual private network, only those aging instruments are connected. So no, we haven't. The private cloud also, upon request from the scientists, sits on our campuses. We don't allow any other sort of access to the private cloud from outside of the campus. We are at this point having capabilities to connect to a public cloud. We work with the MDF, the Materials Data Facility, and the scientists have the right basically to upload the data to the MDF. They decide if they want to upload. And then MDF as a server sitting in, I think, Argonne National Lab, I think in supervision of Professor Ian Foster, they actually are then allowing access to that particular data, but the data is expected to be curated, to be indexed, to be published, accommodated with the publication paper, and so really being ready for usage.
Okay.
But those are some of the really good questions, how far one should consider different private clouds that can create a distributed ecosystem, and then particularly a research team that sits across different organizations, different campuses, would want to privately share among their private clouds the data and have access to each other data. That's a very valid comment, but we haven't done that yet.
Okay. And somebody asked me a question here as well. Does BRACELET have facilities for managing firewall rules remotely? And the reason for this question is newly purchased instruments that are still under support that you want to protect from the outset, but allow a vendor to access in a controlled fashion. And basically a follow-up, can the BRACELET device control what could be forwarded to the instrument computer?
No, not at this point. Yeah, there is some communication, but it's a very controlled protocol in terms of when the authentication happens through the BRACELET, then the feedback goes back, right, through the web HTTP protocol back to the cloud, to the instrument. So again, the amount of the messages, what can be moved, also setting up the local area switch, what MAC address to sort of support, we are really trying to limit it. So no, remotely at this point, you can log into the BRACELET device, but going to maintain, for example, a remote instruments, at this point we haven't looked at it. As I said, we looked at mostly at XP systems because we have several of those instruments, and they're actually, as I said, our IT staff is very worried that malware can come in. But those are very good questions that if we have Windows 7, at some point Windows 10 will come, how should these edges get modified because they will have bidirectional traffic. And then I suspect that these instrument devices might need to have capabilities to check what messages they even just are allowed to process. But at this point, no, we don't have that.
Okay, well, that was all the questions that I had. So thank you again, Klara. This is really great. A couple people have also asked for copies of the slides. So when you get a chance, just send those to me and I'll make sure that they get posted.
Yes. And please provide feedback. We are very interested that as a community, the bracelet, for example, I think that could be a community effort because as I see it, more and more labs have these aging instrument problems. So you could actually work as a larger group on this problem.
All right, well, that sounds great. So thanks everybody for joining today. Next week's talk is going to be Geronimo from Florida International, and he is going to be talking about Amlight. And we'll make sure that we get this posted, the slides and the YouTube video. Have a good weekend, everybody.
Thank you. Bye-bye.